And what we're saying here is, I didn't do that very well. It's not showing up. There it is, exactly null. Let's get rid of that. And let's just bring our hypotheses in here and just say we want to know whether it's on one side of that bound or the other. And we're going to say the probability of being at 0, there's that touch of Bayes coming in there, is 0. We don't believe it. All right? For an example, so for years I've been saying, you know, I really don't care much about correlation. Here's an interval. I'm sorry. I'm off. All right? So I'm going to extend that now to an interval null hypothesis. An interval null. I'm going to say that, well, 0's in the middle of that, but I want some range around 0 to be in effect, all right, no difference. And I need to do this for some mathematical reasons that I won't go into. We just don't have time for that, okay? And it has to do with convergence and those kinds of things. But I need to have a region there that things can converge into if they happen to be in there. So I'm setting up what I call an essentially null region, okay? And we've got the superior and the inferior side, but we'd like to bring those in as well, all right? So you're either in this small region, you can define the small region, we'll have examples where we define it in various ways, or you're on one side or the other. One side or the other. We have basically two one-tailed things working here. Now, what I thought the slide was, I have done this all the time with correlation coefficients, because I've never believed, or I've never understood why anybody cared when they got a p-value out of SAS or anything else, and it told me that this correlation coefficient was different from 0. Like, who cares whether a correlation coefficient is different from 0? I want to know if it's sufficiently strong. Now, my number might be 0.3 in terms of strength, because when I see a scatter plot, it begins to have a little bit of a form at 0.3, but I knew I could probably be safe if I said that there really is no correlation between two things, okay? On a clinical side anyway, all right? Between -10 and plus 10. You can pick any region you want. I just picked this one to get us an example. So what I'm saying is if the measure we're looking at, or the statistic we're looking at is a correlation coefficient, maybe we put an essentially null region between -10 and +10, and then we move those in and we say, hey, if it's greater than or less than that, we're okay. So there's an example. Dr. Chance believes p-values are widely and dangerously misunderstood, all right? And this is a fact. This is an absolute fact, okay? She says, contrary to common belief, the p-value is not the chance that the null hypothesis is true. Not the chance the null hypothesis is true. She continues, both content investigators and statisticians behave as if a p of 0.02 means there's a 98% chance that the null hypothesis is false. All right? I know this is a fact. All right? They behave this way. They see a 0.02, they think, it's about 98% chance that it's false. All right? All right? So the lack of understanding leads to absurdly incorrect interpretations and simply bad decision making. We'll see an example of that. She also believes that Bayesian methods offer great ways to address these issues. But Bayesian methods have been slow to be widely adopted in practice. Why? Well, she says, although the computations involved are now feasible, they weren't when I was in graduate school, full Bayesian approaches require the team to pre-specify more about each question than they seem to be willing or able to do. There's just a lot of front work that needs to go on, all right, in order to get things right. If you just take this classical straight way of even comparing two proportions and you use two beta priors, there's 2 parameters for each beta prior, there's 4 parameters you've got to come up with each question. It's a lot of work. I'm going to show you an easier way that gets us mostly of the way there, almost all the way there, I think. That's what the touch of Bayes comes down to. All right? So Dr. Chance's mission is, in order to get good answers to more useful questions, we need to find a straightforward way to add just a touch of Bayes to common frequentist methods. So what's my rationale here? All right? We've got all these frequentist methods out there that people have been using for decades. They know them, they trust them, they like them, or whatever. If we can spin them just with a little touch of Bayes and turn things around and get them to answer questions that are much better questions than the p-value answers, all right, then we're going to be a step ahead. So that's the mission. Whatever this might be, says Maxine, the pure frequentist will dislike its Bayesianism, all right? And the full Bayesians will think it's simply too simplistic, a cop-out. And I got stories that I could tell you already about that. I talked to Sunil about this about a year ago. He probably doesn't remember. And what he wrote back was in the email, it's right where you ought to be. Right where you ought to be between these two camps. If you can piss both of them off, maybe you're in the right place, all right? So here we go. So Maxine said, the scheme I'm going to show you stems from similar ideas that are now advocated for sample size analysis for study planning. Regarding sample size analysis, so I don't know if you know this paper, but it's written by, well, he sort of needs no introduction in the world of biostat. This is second author here and very much involved in this paper is Marvin Zelen. And Zelen was a pioneer in clinical trials, founder of the Eastern Cooperative Oncology Group at Harvard, basically the founder of the Harvard Biostat Group. And he considers this notion that we're going to talk about today and what they talk about here in terms of sample size analysis as one of the most important concepts that young investigators want to know. I've heard him speak on it. All right? There's another chapter, a chapter that I wrote with my colleague from SAS when we wrote Proc Power and Proc GLM Power. We asked to write a chapter. And the same principles that Zelen talks about in that stat science paper, we incorporated into this chapter. I'd actually been using those principles for a long time. And when that chapter came out by Zelen, I said, oh, now I can do this stuff. I can do this crazy stuff because Zelen says it's okay. All right? If you write me, I can give you a copy of that chapter. I don't put it out on the web because it's copyrighted, but I can give you my LaTeX output, my PDF of my LaTeX. It looks almost identical to the article. All right? If you ever want that. So what's the big notion here? The notion is crucial type 1 and type 2 error rates. What's a crucial type 1 error rate? A crucial type 1 error rate, all right? I'm assuming you know what a regular type 1 error rate is. A crucial type 1 error rate, which I call alpha star, all right? If the test yields traditional statistical significance, if the p-value is less than alpha, what's the chance that this will be an incorrect inference? So we're flipping around, okay? We're flipping around the conditionality of the common type 1 error rate. Now you've got a significant result in front of you. What's the chance that it's wrong? Type 2 error rate, the same thing, all right? Type 2 error rate, the test was not significant. What's the chance that it's wrong? Flipping around the conditionality of a type 2 error rate. People are always asking me, so I've been giving these workshops and teaching these principles for like 15 years. People are always asking me after the workshop or even during it, because it's all about sample size analysis, can we use that same stuff that's talked about in the Lee and Zelen paper, or talked about in the O'Brien-Castello chapter, or talked about in other papers as well, all right? And